Today we move on into talking about sine and cosine as being periodic functions. We've looked at sine and cosine in terms of unit circle and in terms of triangles, but we're going to take a look at them separately just as periodic functions. I'm going to draw the unit circle one last time. Probably not one last time. The sloppy unit circle. And we're going to stick only to radians eventually. When we do these as functions and just look at their graphs and treat them as periodic functions, we will just think of them as radians. So you're kind of born in degrees. Triangles make sense in degrees. Unit circle makes sense in degrees, but we're going to work more and more in radians. Okay, so you can see if this angle theta gets larger. Oops, it's not very straight. So as we start with theta equals 0, it starts down here, and this angle gets larger, goes up and up and up, and goes to 1. And then as it comes around here, it starts going back down to 0, and goes to -1, and then back up to 0. So what it does is this. And in radians, that's 2 pi radians. So we have this graph, and if we keep going, we go around again, we get the same thing. We get the same thing again. If we go the other way, negatively, we get the same thing too. So this is periodic. And there are a lot of phenomena we need to describe. And we can use sine waves and cosine waves to do that. Actually, we can add together sine and cosine waves to get any sort of shape wave. We can even get wave packets. We can get pointy waves, sawtooth waves. And this stuff becomes very important in sound production. Electromagnetic waves are very important. A lot of other fields deal with periodic functions. So we're leaving the context of a unit circle in the context of triangles, and we're just going to talk about sine and cosine in terms of these things. Now, if you were to remember one thing from this year, this would be it. This would be the best thing to remember, I think, what the sine function looks like. Just plain sine of x goes from 1 to -1, and it has a period of 2 pi. It means after 2 pi x go by, which is about 6.28 x, after x goes past 6.28, it starts to repeat. So we have a periodic function. Alright, and that's sine of x. Cosine of x, we're doing this in the x, so you can kind of see it here. I'm going to kind of do the y sideways here. So y starts out so this is y going that way, and this will be, well, actually that's theta going that way. And this is y measured out here. Alright, theta going that way. So when theta starts at 0, y, the cosine of x is 1. And as theta goes up to 90, cosine of x goes to 0. So it does this. It has the same shape as sine. In fact, you can push a sine curve over and get a cosine curve. So if we turn this graph sideways, we get something that looks like this. So it starts at 1, goes down to -1, comes back up to 1, and it keeps going like that, repeating. This is the same shape as this. So if you push this over, so you started here, you can see that this would be a sine curve here. Sine and cosine, pretty much the same function. This pushing things over back and forth, it's called changing the phase. P-H-A-S-E. We'll talk about that in the next one. It's not terribly important as understanding these things here. There are a couple terms associated with this function here, sine of x. We complicate it a little bit more by adding in amplitude and period. Okay, let's take a look at what those do. So, what color? I don't know if this blue works on this beige background. Oh, that was a nice straight line. Alright, so amplitude is the measure of how high it actually gets. This is the amplitude. That's all it means. If you have just the function f of x equals sine x, its amplitude equals 1. And we can put that out front. We can use just about any letter we want. Use A for amplitude. Okay? So if we wanted this to go up to 2, we could have f of x equals 2 sine x. This is the same function, except now it's stretched out. It goes a little higher and a little lower. If it goes up to 2, it goes down to minus 2. Okay? So that's amplitude. And you can have it go less than 1. You can go to 1/2. This amplitude can be 1/2. It can go up to 80. You can scale it however you want. That's what this number out here does to this sine function. It doesn't change the period. If I had something with a smaller amplitude, it would still go to 0 at the same places. It would still have a maximum at the same places. So it doesn't change where this reaches various milestones, if I drew that right. Okay, so that's what the amplitude does. There's 3 different amplitudes here, and they're measured at the highest point. And at the lowest point, they're exactly the negative of that. Okay, the next thing we're going to change is the period. Alright? So if this is, let's do again, sine x, what's this number out here? This is 2 pi. This is about 6.28. Right, we don't do degrees. If there was degrees, that would be 360 degrees. But we try not to do degrees anymore here. We keep things in radians. Alright, so if that's f of x sine x, what is f of x of sine of 2x? Alright, that means when x reaches pi, this will be the sine of 2 pi. So this changes how quickly it goes up and down. In fact, it'll have a period. It'll look like this. Alright, so when x equals pi, if that was 2 pi, this is pi, then it'll have a period of pi. So the period, we'll just use p for now, period equals, well, let's generalize this. So if you have sine of bx, I believe your book uses b, what is the period of this thing? Well, if b was 1, this would be 2 pi, and the period is cut in half by that. So how about it equals 2 pi over b. Alright? Period equals 2 pi of this number over here. Alright, does that work out? Let's see. The period, in this case, is going to be 2 pi over 2, which does indeed equal pi. It works out, and this is sort of a general formula you can use. If you have a b here, if you have some number here multiplying the x, and we'll talk about frequency later on, to get the period, you take 2 pi and you divide it by that number. Alright, that number could be 1/2. Really quickly, I'll do a sine of 1/2 x. You don't have to think about it. You can just plug it into this formula. What's the period of that going to be? It's going to be 2 pi over 1/2. You can flip and multiply, and that becomes 4 pi. Alright, so this is a curve that has a period of 4 pi. Let's write it as red. So what would a 4 pi one look like? Well, it'll reach half a period at 2 pi, so it runs off our graph here. Oops, let me start a little steeper. It looks like this. And 4 pi, this is 2 pi here, 4 pi would be like way over here. So that's where we come back up. Okay? These don't have to be integer numbers. We often like them to be integers, so it works out to nice units of pi. You could have sine of pi x. You might often see that. In which case, period is going to be 2 pi over pi, or just 2. So this would be a function that when it gets to 2, has completed 1 period. Alright? Good. So that gets us started working with sine functions. Extremely powerful functions that we use to model all kinds of things, all kinds of periodic things.